Lessons Learned Towards a Transgressive and Transdisciplinary Pedagogy for STEAM Students, presented by Dr. John Cribbs, Wentworth Institute of Technology, Boston, Massachusetts, and Joshua Gigantino, MSD, Arizona State University, Tempe, Arizona.
My name is John Cribbs. I am an assistant professor of construction management at Wentworth Institute of Technology in Boston, Massachusetts. I have a background in architecture, construction management, and environmental design, and have previously worked as a building science consultant. My interests lie in interdisciplinary learning techniques, pedagogies, and curricula, and I have worked with various architecture students and construction management students through multiple lab environments.
My name is Joshua Gigantino. I'm a PhD student in Arizona State University's School of Arts, Media, and Engineering. I have a Master of Science in Design in New Product Innovation from ASU's Design School and a background in industrial design, digital fabrication, animation, and marketing. I specifically study aspects of human body mapping that have been used in developing spacesuits and other pressure suits, and further applications of these so-called lines of non-extension. I am not interested in erecting a building, but in presenting to myself the foundations of all possible buildings. Wittgenstein. How do we extend what works well in physical, studio-based, in-person, and hands-on education into the digital realm while compensating against issues that repeatedly arise in digital formats? The two of us have been working in hybrid online and offline projects for many years. Some things work well in person that don't translate well to online and vice versa. We aim to extract some of these lessons learned to apply to digital tools, daily praxis, and online pedagogy. Along with teaching design as practice, research, and thinking methods, we propose a higher level of understanding of design according to Buchanan's 4 levels of design and Friedman's operationalized research frameworks. A very quick overview. In 1992, Buchanan proposes 4 levels of design, starting with the visual and symbolic, leading into objects and artifacts. Following that is what we would now call experience design, or as he puts it, activities and organized services, and at the 4th level, quote, complex systems or environments for living, working, playing, and learning. We would like to combine this with Friedman's research frameworks, which include basic or fundamental research, applied, adaptation, clinical, diagnostic. To teach these 4 levels of design and 3 research frameworks to designers and non-designers as part of an integrated exploration learning curriculum. This would be a functional but formal academic research combining the best of design, psychology, and anthropological methods. Design education in this new context encompasses a wide array of knowledge domains by necessity. No longer is architecture a singular pursuit. The architect must understand management, economics, electronics, some elements of the underlying issues in a software-driven world. Same for the industrial, graphic, or interior designer. These integrative skills extend in reverse through other academic fields as design thinking and exploration education. Design becomes a strategic asset in business, again, starting with design thinking, but extending to more nuanced aspects of design. The era of design as afterthought has to come to an end because designers of all kinds are productive constrictions in development of artifacts, systems, and symbolic elements. Early strategic design produces better and more sustainable outcomes at all levels. We would like to teach design as this strategic asset across all enterprises. In analyzing our own projects, we attempt to integrate with control a new form of transdisciplinary education that recognizes and practices what worked in the past in new ways. For this analysis, we look at several recent projects and derive lessons from them. First, Dr. Cribbs' work in pushing digital sensing and fabrication into the field of construction management through the use of an augmented reality sandbox for teaching undergraduates about issues around construction site fill, and his work bringing 3D printing into site planning. Next, Mr. Gigantino's work in futures narratives and design research are briefly covered. These include the celestial gaze photoelicitation method and a quick overview of the Luna City 2175 project. Due to the pandemic, the Teotihuacan apartment compound project is temporarily on hold. Finally, we will cover the recent VIMS 2020 Datathon, a fast competition in BIMS modeling and VR visualization.
The augmented reality construction management sandbox was utilized to teach introductory courses related to blueprints and civil drawing analysis and reading. Many students have never seen these types of drawings before, so lifting 2 dimensions into a 3-dimensional mindset becomes very complex and difficult for students to grasp. The augmented reality sandbox allows us to bridge that gap quicker and allows the students to start visualizing 2 dimensions and 3 dimensions simultaneously. It's a combination of sensors and visual projections. It's a hands-on tool that allows us to begin modeling site conditions themselves as they relate to the provided drawings, and provides real-time response and feedback loops for the students as they begin to morph and change the sand within that sandbox. So as you can see from the video, as you change the landscape inside of the sandbox, the contour lines move and match in real time. This provides students a great understanding of what's happening with highs and lows, steeps versus shallow slopes, and catchment and drainage. From that video, you could see that you could introduce water into that particular landscape, and you can see some here in this static photo where that water moves to the low points. Therefore, you can replicate drainage patterns across a proposed civil site plan. The first lab activity that we undertake as one of the courses at Wentworth Institute of Technology is to model existing conditions provided on a drawing. This allows the students to read the topo maps, understand those highs and lows, provide analysis of where each one of those should be located and to what depth, and then they begin to understand how to read that existing condition based off of a 2-dimensional drawing. From there, the second lab activity is to model existing conditions again, but then regrade for a proposed design condition. This allows them to develop a basic understanding of earthwork, ideas such as cut versus fill, which will then bleed over into an estimating course the following year, and then the idea of stockpiling materials for construction site logistics. All of this is done through the augmented reality sandbox and provided flat 2-dimensional PDF drawing sets, which are plotted to scale for the students to begin reading and understanding. Here's a look at that proposed condition and the existing condition underlay. So you can see how the students are required to model initially the dashed line condition, which is the existing, and then update the topography to match the proposed design condition with the solid topography lines. This allows us to understand whether or not they've created a flat building surface with drainage around that building foundation, and then the amount of soil or sand in this case that was moved gives them an insight into the amount of dirt or earthwork that would be required for this particular job. When going through these activities and exercises, a survey was deployed prior to engaging the augmented reality sandbox, just going off of typical lecture material. And that same survey was then delivered following the augmented reality sandbox activity. You can see here in this particular matrix that there was an increase across the board in the percentage of students responding correctly to questions following the AR sandbox activity. Particularly, the ones of focus are what does it mean when contour lines appear to be equally spaced? You can see there's about a 23.5% increase of students understanding what happens when you have equally spaced contour lines. And then the biggest component here is denoting the difference between a solid contour line and a dashed contour line. This really allows the students to understand how to read the layers within line work on a civil drawing plan. Additionally, following the AR sandbox activity, a Likert scale was deployed. And what you can see from here from the responses across the student sections was that they were able to visualize contour maps following the AR sandbox activity more so than just following the lecture. And that the AR sandbox alone became a very beneficial component or tool for teaching this particular component of drawing visualization for those particular students taking construction blueprint reading courses. Tagging along with this, the CM 3D printing, construction management 3D printing activities that were done allow students to really begin to understand how to lift floor plans into elevation and begin understanding the importance of section drawings. The 3D print was engaged to show students how a drawing from a floor plan view is lifted in multiple dimensions and then sliced backwards into print layers so that you can ultimately end up with a physical component from a 3D printer. This allows them to have an association of a plan view into the various elevation views from front, back, left, right, or plan northeast, southwest, as well as the top and the bottom for those particular plans. This introduces the idea additionally of transverse and longitudinal sections. As they begin to cut through models and they begin to look at simple geometry, they're understanding the height relative to each layer of that print, which associates to various levels of plans themselves. Following the 3D printing activity, a series of surveys was deployed similar to that AR sandbox activity, where in this case we asked the difference between pictorial drawings and multi-view drawings, and the students were able to showcase an increase in correct answers across the board here, looking at denoting the different types of drawings and the importance of each type of drawing. Additionally, looking at the principal views for a multi-view drawing had the largest jump in percentage increase for which students felt confident and responded correctly, which again shows that there was a higher level of understanding between how you lift plans into elevations and the importance of each different elevation when rendering a specific component or building or design assembly. Finally, a Likert scale was delivered at the end of the 3D printing activity, where the students were asked whether or not the lecture content and material in tandem with the 3D printing or the 3D printing activity itself was more beneficial. And what we can see here is that both lecture and the 3D modeling or 3D printing component and activity were beneficial. And following the 3D printing demonstration, they were able to visualize multi-view and pictorial drawings at a higher level than just from lecture material alone. So this was very encouraging from a multimedia use standpoint when dealing with teaching students how to read various drawings, floor plans, elevations, and introduce the idea of drawing sections.
The celestial gaze method by Dr. Trinidad and Mr. Gigantino consists of two complementary systems of exploring future narratives through subject image generation and narration. The first method uses a series of cards of planets and other celestial bodies in a photoelicitation technique in which participants select images and then use those cards to tell a story of their future in outer space. The second method involved middle school students drawing images of their futures in outer space and narrating them on video. Further analysis has shown this method to be a powerful tool for describing what Taylor in 2004 calls social imaginaries as applied to futures narratives. The first celestial gaze method is relatively simple. The research participant is presented with a grid of images. They then select a series of these images, usually 6 out of 36 possible images, and narrate them. This technique is referred to as photoelicitation. It was pioneered by Collier and Collier, documenting life in rural Canada in the mid-20th century. The data generated by the celestial gaze method is used in 3 ways. The first and original use is to render statistical information on the participant's perception of imaging technology as it changes through time as viewed through space imagery. It can be used to generate narratives about space futures that are then utilized for ethnographic analysis, which proved a more useful aspect for Dr. Trinidad's dissertation work. Luna City 2175 was Arizona State University's annual Emerge Festival for 2018, with author Kim Stanley Robinson as artist-in-residence. Luna City is a futuristic space simulator in a theatrical setting, or serious research as play. Luna City presents a future in which people live, work, and play in a giant crater at the lunar South Pole. A parametric city of robotically built sandbag domes and tubes stretches into the night, providing shelter and habitat for tens of thousands of inhabitants and guests. Over the course of a weekend in March 2018, approximately 900 people experienced the lush regolith and bamboo environment, rich graphical treatment, and experienced a slice of life with several dozen actors simulating daily life on Earth's nearest neighbor. The Luna City process started as a series of formal thought exercises among an ad hoc group of writers, space scientists, dramaturgs, artists, designers, and engineers. Over the course of 8 months, it involved nearly 200 people in the creative process. Work was conducted in person, in real-time conferences online, and through an extensive Slack and Google Drive infrastructure. Sketches and concepts became structures, performances, costumes, and a living block of a space city in that time. Design of Luna City's built environment iterated rapidly across student teams handling construction artifacts, costumes, systems, wayfinding, and animations. The ability to work seamlessly with multiple studios across the university and beyond using online tools enabled complete systems to be generated from sketches and simplified feedback. Student developers were afforded considerable autonomy toward look, feel, and function as long as their work functioned with others' designs. This created a layered, lived-in, and vibrant feel to the city. One interesting aspect of Luna City was the SME undergraduate capstone project. This was a year-long offshoot of the Luna City project. SME involved creating a technically and geographically realistic second lunar habitat in Unity VR, complete with population, life support, and a garden dome. A series of animated augmented reality posters and a bit of futuristic real estate salespersonship completed the project. It was developed both face-to-face and using online tools such as Slack and Google Drive. SME was showcased in the lobby area of Luna City and at the School of Arts, Media, and Engineering's Spring Showcase.
The VIMS 2020 Datathon was an interesting competition in which students were engaged to create a building information modeling from a provided set of architectural, structural, mechanical, electrical, plumbing drawings. The students engaged in this particular project could be from the same university or different universities, and in our case, the students spanned Wentworth Institute of Technology in Boston, Auburn University, and Arizona State University out in Tempe. So not only were we constrained by location, we were also constrained during the pandemic by digital-only communication and strategies for sharing information and data. This was held during February and March of 2020 during the mass pandemic quarantine. So again, the idea here became that students were only able to work in remote situations through digital means and communication, which made things a little bit more difficult on top of the fact that we were working with students across the entire United States. Ultimately, the students were able to develop a very high-level building information model from the given information set of drawings through the use of collaborative cloud-based software packages and building information modeling authoring tool, as well as open source gaming engines, and simultaneously working in each one of these media to generate flybys, to generate virtual reality components, and ultimately the finished product for this particular competition. The lessons learned from this particular competition were the differences between dedicated teams and distributed teams became quite noticeable. Dedicated teams that are in the same location are able to accomplish things a little bit quicker and in a more narrow scope. They have obviously worked together previously, and if they haven't, they have the opportunity to team very, very quickly. The competition that we went up against had dedicated lab equipment for architectural and VR components, and many of the students had domain-specific skills. Distributed teams had an interesting, in our case, an interesting outcome where we had an ad hoc team of various levels of academic students through multiple disciplines of education. We had architecture students at the bachelor's and master's level. We had construction management students at the master's level, and then we had arts, media, and engineering, AME students across master's and PhD level as well. So we had an ad hoc team from multiple universities with a mixed skill set, and we were able to produce at a very high level, even given the constraints from a distance and a digital only platform. Regarding conclusions and takeaways from all of these various projects and labs, one of the main things that sticks out is the idea of speed of knowledge. And speed of knowledge seems to be the singular factor in stimulating thought. And what's meant by speed of knowledge is, in the digital age, students seem to want to know the end product at the beginning of their learning process. So by showing them what something can be at the very end of a process and introducing the fundamental basics at the beginning, and expediting that middle component and sort of showing the students how they can arrive at that final product or process, allows them to think through problems a little bit differently. The idea comes to mind very specifically when we're looking at 3D printing. There's an immediate product that is produced through a handheld piece of geometry or building that comes out of the 3D printer. But in order to get there, you need to understand the various types of drawings and modeling techniques that went into that product. By introducing the idea of a plan, elevation, and section view to the students, and then printing something and showing them how they all combine and come together in the real world for a three-dimensional handheld component, the students were able to really understand how to bridge the gaps between the various disciplines, the various components of the drawings, and why things were important when layered information is being explained on very different sets of drawings. So speed of knowledge, showing students the fundamentals and the final product at the same exact time, and then reverse engineering that middle ground seems to be something that was a common thread across all lab components and all of the projects that have been previously explained in this presentation. Tools are also important, but it's very important to keep the attention span of the students. So again, that ties back to the idea of that speed of knowledge. Additionally, one of the main takeaways for many of these projects is the idea that software doesn't solve everything. Many students, again, like the idea of a push-button solution. But in order to arrive at a true push-button solution, you need to understand the fundamentals behind the scenes. And again, the idea of that speed of knowledge is showing the students the importance of the variables that go into that push-button solution so that they can manipulate multiple software packages, data streams, or tool sets in order to accomplish what they're looking to accomplish at the end of that particular project.